faces the same baseline threat: continuous friction with a chaotic, shifting environment. Left unchecked, this constant interaction leads to systemic collapse, taking the form of parasitic energy loss in a circuit, mechanical fatigue in a joint, or sensory hyperarousal in the human brain. Across entirely disparate fields, from telecommunications to clinical neurobiology, stability relies on a specific, repeatable structural alignment. Looking at this matrix, the pattern of that alignment becomes visible. The framework dictates that to manage the chaotic element on the left, a foundational interface must be deployed in the center. That interface absorbs environmental friction, generating a stable systemic output on the right. We can trace this exact progression across 4 distinct physical and biological domains. The materials operating within this matrix are not passive building blocks. Their intrinsic atomic properties actively regulate the function of the entire system. Recognizing this alignment allows for the engineering of stability out of environmental noise, regardless of discipline. At the nanoscale, we see this matrix applied to next-generation programmable nanophotonics. The chaotic element at this scale consists of disordered atomic states, which trigger continuous power dissipation and parasitic optical absorption. This is a Mach-Zehnder interferometer. Applying an antimony-based phase change interface shrinks the modulation length to a 5 micrometer footprint, locking into a stable state. At the 1550 nanometer band, this drops the absorption profile near zero. This level of phase control is achieved with an energy footprint of only 10 femtojoules per cubic nanometer. At the atomic level, the molecular structure of these chalcogenide lattices forms a physical barrier, protecting the optical signal from parasitic loss. The second row of the matrix scales the framework up to physical solid-state architecture. Here, the chaotic element is rigid geometric constraints. Moving copper paths suffer structural fatigue and eventual failure when subjected to physical stress. This RF antenna utilizes a room-temperature gallium liquid metal interface. When a low-voltage pulse hits, the fluidic metal deforms, flowing without fracturing. These potentials alter interfacial tension, allowing the circuit lines to actuate and self-heal during reconfiguration. The systemic output is a highly elastic conductor that bridges the mechanical gap between stiff semiconductors and pliable environments. In solid-state physics, a fluidic interface manages mechanical wear by adapting to physical stress rather than resisting it. In the third row, the matrix maps onto macro-architectural and biological systems. For an ancient structure like the Tabernacle sanctuary, the chaotic elements included shifting desert sands, high wind vectors, and organic decomposition. Exodus 26 describes a foundational interface of exactly 100 interlocking solid silver sockets. This creates a uniform structural barrier against the shifting wilderness terrain. This silver matrix isolated the internal organic components from the ground, preventing the progression of structural decay. This architectural layout shares a functional mechanism with modern biophysics. Silver possesses the highest electrical and thermal conductivity of any element. Its atomic structure facilitates rapid donation of free electrons to disrupt microbacterial respiratory chains. This same mechanic is utilized in modern clinical wound dressings and matrices to suppress medical-induced tissue inflammation. The 3,000-year-old architectural framework utilizes the same biophysical properties that modern medicine relies on to isolate organic tissue from environmental decay. The final rows apply the matrix to human neurobiology and cognitive growth. The chaotic element in this domain is multi-channel sensory noise and unstructured environmental data. Without an interface, this noise forces the autonomic nervous system into a state of hyperarousal and cognitive exhaustion. In clinical practice, Ayer's sensory integration serves as the biological interface, organizing multi-channel inputs into structured modules. Strict adherence to these measures yields high goal attainment scaling, stabilizing the autonomic system and improving motor balance. Cognitively, generative AI serves as a similar scaffold, filtering semantic noise from high-density materials to prevent executive strain. Focused inquiry and data filtering function as active internal organizers, serving as the protective foundations for the human mind. When the complete structural alignment matrix is brought together, the correlations across each layer become visible. Following the systemic output column shows a consistent result: low-loss optical control, self-healing circuitry, non-decaying environments, and neural equilibrium. Whether managing thermal pulses or vestibular inputs, the underlying mechanism of order remains exactly the same. Structure regulates function. While the chaotic element of an environment cannot be eliminated, it can be buffered by a precisely engineered interface. Applying these principles with technical precision is the core of structural stewardship, the deliberate construction of stability from chaotic noise. Ultimately, maintaining function relies entirely on the strength and elemental composition of the foundational interface.